So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to be proving the functional equation of the Hurwitz Zeta function, right? Basically, this is the functional equation, and that we are going to prove in this video. But first of all, let me just remind you that I have proved the functional equation of the Riemann zeta function as well, right? Although I'll just paste the link of the video, like of that video, in the description box of this video, and I would request to just watch that video once, because we have used a lot of things like Jacobi theta function and some sort of Mellin transform, some Poisson summation formula. So we have used a lot of stuffs in that video, and I would say the Hurwitz zeta function is easier to prove rather than the Riemann's zeta. I'm sorry, the functional equation of the Riemann's zeta function, right? Because we don't need some any sort of like Mellin transform or Jacobi theta function or like Poisson's summation formula, right? It's just straightforward. Just we have to use the Fourier series, right? And we are very well known in that field, right? So I think it's not gonna be difficult to prove this down. But yeah, we will use some sort of beastie integrals as well, but it's not beastie, but yeah, it's useful, and I'll prove them in the middle of in between of this video. So I'll prove that all, don't worry about that. Okay, so first of all, you know that we are just gonna prove this with the help of Fourier series, right? And you are very well, like you must guys are familiar with that, right? So I don't need to just explain it to you again, right? Okay, so basically it's a infinite series representing a function, like in an interval, I would say. Yeah, right. So basically, for our case, let's say capital F of x comma s equals the Hurwitz zeta function, actually, which is the summation as k goes from 1 to infinity of 1 over k plus x to the s. So this is our function, right? And we are just gonna play around with this function only throughout the video. Wait a second. Yeah, now it sounds good. Okay, so we know that the Fourier series representation. So Fourier series representation of a function, and we are just considering this function in some sort of interval of, let me just give you the interval as well here. So since s is, we will consider s as a constant, right? So it's not of any sort of variable, and x is variable, so it will be just lying between 0 and 1. Okay, so Fourier series representation of capital F of x comma s. So it's capital F of x comma s equals a naught over 2 plus the sum as n goes from 1 to infinity of a sub n cosine of 2 pi nx plus the sum as n goes from 1 to infinity of b sub n sine of 2 pi nx. So this is the most fundamental function, the Fourier series representation of a function, and I would like to just cover it in this red box because it's important. So yeah, and if we talk about the coefficients, that is a naught, so it's the integral, actually 2 times integral from 0 to 1, the bounds actually which we have given earlier, that is this bound, right? 2 times the integral of f of x comma s. Basically you have to integrate the function, right, in order to find a naught after just multiplying some factor as well. So it's 2 times integral from 0 to 1 of the sum as k goes from, I think it's 0, I think we should have considered 0, I think, I'm not sure, but let's just consider 0 because the the Hurwitz zeta function is beginning from 0, not from 1, as of the Riemann's zeta function, right? So it's 1 over k plus x whole to the x dx, right? And yeah, so this can also be written as 2 times this infinite sum and integral from 0 to 1 of 1 over k plus x whole to the s dx. Now, okay, if we try to just integrate this with respect to x, so this can be this wait a second, so this can be integrated to, because if we try to integrate this, wait a second, this is k plus x whole to the minus s, right? So this can be written as k plus x whole to the minus s plus 1 over minus s plus 1. And we can say, since k is going from 0 to infinity, wait a second, I think it's gonna be 0, right? Because yeah, it should be 0, right? I'm not sure. Okay, wait a second, let me just prove it to you. I think I just got it. Well, you can say a theory or a lemma, you can say a lemma which says, well, this can be written as 2 times integral from 0 to infinity, since this sum is going from 0 to infinity, so we can just plug k plus x equals any variable. Let's say k plus x equals t. So when x equals 0, t equals and when x equals 1, so it's t equals k plus 1, so it's k plus 1. And the sum is going from k equals 0 to infinity, so basically that's going to be integral from 0 to infinity of 1 over t to the s, right? So basically it's 1 over t to the s and dt, actually dt, and where t is k plus x. So a lemma says, which can also be written as 2 times integral from 0 to infinity of t to the minus s dt. Basically it sounds divergent, right? It sounds diverging because this is not a proper integral, I would say. So in terms of higher mathematics, like if we talk about higher mathematics, so integral from 0 to infinity of u to the alpha du, we consider it to 0 and when alpha is not equal to -1. Basically this is what it is, so we have to just consider this. It's a lemma, you can say. So basically this is saying that a naught is coming out to be 0, right? Yeah, well, we can talk about that later on, but not now actually. Okay, now let's talk about the second second coefficient, which is a sub n. So it's 2 times integral from 0 to 1 of capital F of x comma s cosine of 2 pi nx dx. So what we are having, it's 2 times integral from 0 to 1, this sum as k goes from 0 to infinity of 1 over k plus x to the s cosine of 2 pi nx dx. Yeah, that sounds good, isn't that? So yeah, what we are having here is, we can say, let me just copy that down again once more here. It's this sum as k goes from 0 to infinity of integral from 0 to 1 of cosine of 2 pi nx over k plus x whole to the s dx. Now we are just going to use some u sub here. Let u equals k plus x, right? So if you talk about the derivative, so it's dx, and the bounds are gonna be k plus 1 and k, right, respectively, the upper and lower bounds. So that's gonna be, wait a second, look here, your x is gonna be u minus k. So let's just talk about that. So cosine of 2 pi n u minus k. So basically it can also be written as 2 pi n u minus 2 pi n k, right? And since 2 pi, like n k are natural numbers, so basically it's a factor of 2 pi, which will give us 1. So basically this can also be written as cosine of 2 pi and u only. So there isn't any sort of change. So right, so basically a n is coming out to be 2 times integral from 0 to infinity, and we have just used the infinite sum over there, and cosine of 2 pi and u over u to the s du, right? And similarly if we talk about the same process that we have went through for a sub n, we can talk about the b sub n as well here. That's gonna give us cosine of 2 pi and u, 2 times integral from 0 to infinity, sine of, wait a second, sine of 2 pi and u over u to the s du. So these two things what we are having so far, and now let's just talk about them. So basically we can just say that there we can, in both the cases we can just we can consider let 2 pi and u equals t, right? So basically if we talk about the bound, so infinity is gonna be infinity and 0 is gonna be 0. And if we talk about du, so it's gonna be dt over 2 pi n, right? So basically a sub n is gonna be integral from, wait a second, we had 2 factor as well, integral from 0 to infinity of cosine of t over, it's t over 2 pi n whole to the s dt over 2 pi n, right? Well, since we can consider isolating u from here, so it's gonna give us u equals t over 2 pi n, right? So yeah, we can just consider you doing that. And here we can say that's gonna give us it's 2 times 2 pi n to the that's gonna give us s minus 1, I think, I'm sure. And yeah, integral from 0 to infinity of cosine of t over t to the s dt, right? Or more precisely, we can consider writing this as 2 times 2 pi to the s minus 1 n to the s minus 1 integral from 0 to infinity t to the minus s cosine of t dt. And we'll talk about the integral in a little bit, but before, let's just talk about the b sub n as well. So basically with the same way we can talk about b sub n, so that's gonna be 2 times 2 pi to the s minus 1 n to the s minus 1 integral from 0 to infinity t to the minus s sine of t dt. So similarly it ain't gonna be changing anything, right? So basically that both the cases are same. Now let's talk about the integral. So we are having some 2 integrals or which we have to evaluate. So let's just talk about the first integral, I sub 1, integral from 0 to infinity of t to the minus s cosine of t dt. And this can be written as a real part of integral from 0 to infinity of e to the I t to the minus s dt. And how did I did that? So basically we know that e to the I z equals cosine of z plus I sine of z. So basically this argument is known as the real part of e to the I z, and this not including the I, so this part is known as the imaginary part of e to the I z. So therefore we can say it's a real part of this e to the I t, which is gonna give us cosine of t that we had earlier, right? So we because just because we have to just relate this in some sort of gamma function, that's why we are doing these things. So basically I1 can also be written as integral from 0 to infinity, or let's just consider using some u sub here. Let it equals x, so I dt equals dx, right? So oh no, I'm sorry, I did messed up something here. Actually ix equals t, and I dx is gonna be dt, and bounds will be same, right? So basically our I sub 1 is gonna be real part of integral from 0 to infinity of e to the I t is gonna be e to the I times, basically it's gonna be, wait a second, t gonna be I, so I x, right? And I squared is -1, right? So we're just gonna use that in the next step. And t equals I x, so I x to the minus s, wait a second, I did forget the I dx, right? So yeah, so basically I1 is gonna be real part of this integral from 0 to infinity, and it's gonna be e to the minus x, and it's I to the minus s, x to the minus s, and it's I dx. So basically it's gonna be real part of I to the, wait a second, I don't need to just grid off some spaces. Okay, here it is. I to the 1 minus s, integral from 0 to infinity. This can be written as 1 minus s minus 1, right? Basically we would be getting rid of this ones there. And why did I did that? Because I just want to relate it with gamma function, as I just mentioned earlier as well. So it's e to the minus x dx. Now let's just talk about the gamma function, and we have talked about this a lot of time, like multiple times. So it's gamma of z equals integral from 0 to infinity of t to the z minus 1 e to the negative t dt. And if we replace z with 1 minus s here, so it's gamma of 1 minus s equals integral from 0 to infinity, and it's t to the 1 minus s minus 1 e to the negative d dt. And exact thing we are having here. So this can be written as gamma of 1 minus s. So basically I sub 1 is coming out to be real part of I to the 1 minus s and gamma of 1 minus s. And so this can also be written as gamma of 1 minus s, the real part of I to the 1 minus s. And from the Euler's formula we can say I equals I pi over 2. So this is a well-known formula. You can derive it as well. Basically when you plug like in the equation, in this equation actually, when you plug z equals pi over 2, so cosine of pi over 2 is 0 and sine of pi over 2 is 1, so that's gonna give us e to the pi over 2 is 1, right? So we can just replace it with that, and basically we are having I1 as gamma of 1 minus s as real part of e to the, well, we can say I pi over 2 times 1 minus s, and that can further be written as gamma of 1 minus s, and it's a real part of e to the I pi 1 minus s over 2. Now let's just talk about the Euler's formula again. Euler's formula. So we have e to the iz equals cosine of z plus I sine z, right? And if we consider, let me just write this down a little bit there, and this thing, I'm not just looking at this properly. I hope you guys are clear with that, or else oh wait a second, you guys are clear with that, I know that. Okay, so now here if we replace z with pi over 2 minus pi s over 2, so basically this is what we are gonna do here. So it's e to the I pi over 2 1 minus s equals cosine of pi over 2 minus pi s over 2 plus I sine of pi over 2 minus pi s over 2. And if we talk about the real part of this thing, pi over 2 1 minus s, so basically that's gonna that's we would be just getting rid of this term actually, because that's imaginary term. So we would be having cosine of pi over 2 minus pi s over 2, and that can also be written as sine of pi s over 2, because cosine of pi by 2 minus theta is just sine of theta, right? And so for the sine of pi by 2 minus theta is cosine of theta, so it's vice versa actually. And similarly, so basically we are here with our first result. I1 is evaluating to gamma of 1 minus s sine of pi s over 2. So similarly, if you try to evaluate for I2, which we had here, so this was your I2 here, so you just have to play with imaginary term, and in the end you would be having I2 as gamma of 1 minus s cosine of pi s over 2. So I maybe I would request you to just do it by your own, because maybe you would be learning something out of it, right? So yeah, let's just plug all the things that back in a sub n and b sub n, and we are having a sub n as 2 times 2 pi to the what we had s minus 1, right? So it's s minus 1 n to the s minus 1 gamma of 1 minus s, and we are having sine of pi s over 2. And if we talk about b sub n, so it's coming out to be 2 times 2 pi to the s minus 1 n to the s minus 1 gamma of 1 minus s cosine of pi s over 2. So that's the beastie things we are having so far. And now let's just get back to our Fourier series representation. So we had f of x comma s as a naught over 2 plus this sum as n goes from 1 to infinity of you had a sub n cosine of 2 pi nx plus this sum b sub n sine of 2 pi nx actually, right? And now we know our f of x comma s was the sum as k goes from 0 to infinity of 1 over k plus x whole to the s, and your a naught was 0 and equals this sum as n goes from 1 to infinity. I'm just going to consider this like a whole sum, I would say, like a common sum you can say, because we just got rid of this term, so we are just having two sums, which I can just write this down a single term and just writing all the terms respectfully. So basically a sub n is being evaluated to 2 times 2 pi to the s minus 1, and it's n to the s minus 1, or we can say this to n to the 1 over n to the 1 minus s, right? And gamma of 1 minus s and sine of pi s over 2, and we are having this factor cosine of 2 pi nx, so cosine of 2 pi nx as well, and plus 2 times 2 pi to the s minus 1 over n to the 1 minus s gamma of 1 minus s cosine of pi s over 2, wait a second, yeah, pi s over 2 and sine of 2 pi nx. Okay, so now we can say this is the Hurwitz zeta function, so it's x, the Hurwitz zeta function of s comma x, or we can say x comma s as well. So basically it is being evaluated to this sum. Well, we can just factor out some stuffs like this one is not depending to n, and this one is not depending to n as well, this one and this one is not depending to n as well, and rest of the things would be inside a sum. So basically it's 2 times 2 pi to the s minus 1 over, no, not over, but yeah, gamma of 1 minus s, or maybe we can consider writing this as 2 times gamma of 1 minus s over 2 pi to the 1 minus s, and times, wait a second, let me just make it in a manner, now it sounds good, and we are having sine of pi s over 2 cosine of 2 pi nx, and don't forget the factor n to the 1 minus s, and this is inside the common sum, and cosine of pi s over 2 sine of 2 pi nx over n to the 1 minus s. And now finally we can just split this a little bit. So basically this is 2 times gamma of 1 minus s over 2 pi to the 1 minus s, and it's this sum as n goes from 1 to infinity. Wait a second, we can just we can write this as this thing sort of. Wait a second, let me just write this. So we can write this as sine pi s over 2, since it's not depending on n, and it's cosine of 2 pi nx over n to the 1 minus s, and then plus cosine of pi s over 2 times this sum as n goes from 1 to infinity of sine of 2 pi nx over n to the 1 minus x. And this is your final result for the Hurwitz like functional equation of the Hurwitz zeta function. Isn't it amazing, guys? Like literally we didn't use any sort of difficult stuffs like we did use in the proof of the Riemann's one. Like this was easy and it wasn't tough at all. So yeah guys, that's how mathematics is all about, and let me just take you to the very first page. So that's what we have to prove, and now we are done with the proof as well. And yeah guys, actually you know why I'm just doing all the things. There are two reasons. The first one is to learn in mathematics, and the second one is I'm just working on the Kummer series. Actually one of my subscribers just requested me to just make videos, and I think this is the last prerequisite, or maybe second last prerequisite, like this video. And do you remember I had proven the two sums as well? The first one was this sum as n goes from 1 to infinity cosine of 2 pi nx over n, and that was, I think I did it to ln of 1 over, wait a second, ln of 1 over 2 sine pi x. And the second one was actually 2 pi nx over n. This was pi times 1 over 2 minus x. So these three things, and the functional equation of the Hurwitz zeta function, these three things. And I have another one thing actually as prerequisites for the Kummer series of the natural logarithms, right? So basically I'm just covering up these things in order to just be clear with the Kummer series later on. So yeah, and I would be pasting these all things inside a playlist which would be titled as Kummer series, right? And I don't want to just prove it to you like yeah we did that and we did use a lot of things without knowing the proof of all these things, but I just want you to just look at all the things proven by me, obviously proven by mathematicians but explained by me, actually not jumping off but learning out of it, right? So again guys, if you got to learn something from this video, just make sure to like, subscribe and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. I'll be there to reply over your questions. And yeah, I would request you to just think about this, because still I'm just suffering with this, and it's quite undigestible, I would say. Yeah. Okay, goodbye guys, take care, love you. And I'm just waiting this video to reach up to 30 minutes. Wait a second, here it is. Goodbye guys.